Am I audible and is my screen visible to everyone?
Sure.
You can mute yourself again. Okay. So, good evening, everyone. Welcome to the sixth live session. Welcome to the sixth live session for the course Concrete Technology offered by NPTEL. So, I am Harshit Agrawal, a PMRF PhD scholar from the Department of Civil Engineering, IIT Bombay, and I will be conducting weekly live session for the entire course duration. So, first of all, for those who have joined the session for the first time, so what are these doubt clearing and interactive session all about? So, these are weekly interactive session that are held every Tuesday from 6 p.m. to 8 p.m. And during these sessions, we interact by answering to the questions that I will ask in the chat box, by posting your queries in the chat box, or by raising hand, unmuting, and asking your queries. Apart from the session, you can always use the discussion forum of the course where you can ask your question and which will be addressed there itself or in the next session. And attending these sessions regularly will help you to answer the graded assignments easily and will help you to further understand complex topics holistically. So, in today's session, we'll first revisit the last live session that was for week 5 content, just a quick recap, and then we'll look into the week 6 content, the things covered in the week 6 content. So, in week 6, we discuss with the discussion that we'll have will be in continuation to the previously held discussion on the mixture design of concrete, which is like divided into following subsession for today's discussion. So first we will discuss ACI 211 method of mixture design. Then we will compare standards like Indian standard, DOE method, and ACI method for mixture design. Then we'll talk about mixture design based on packing density and rheology. Then we will move into batching of concrete and mixing of concrete. In between, we'll have some numerical questions as well as some objective question to address related topics, which will challenge your understanding of the concepts. And finally, we'll conclude the discussion and I will try to address any other queries post discussion. So, last week we concluded with the week 5 of the course where we talked about mineral admixture mixture design of concrete. We first had a basic overview of mixture design where we talked about different components that are involved in a concrete mixture design. We then saw how different desired properties of concrete like fresh state, hardened state, and durability performance, how they are dependent upon these different mixture design components. Then we discussed about target mean strength and characteristic compressive strength. What are they and how are they calculated and how they contribute to the mixture design of concrete. Then we started discussion on mixture design based on standard provisions, where we first had an overview of IS 456 code in how it provides guideline for concrete mixture proportioning to achieve a desired strength, durability, and workability. We saw different tables and clauses present in IS 456, which forms the guidelines for the mixture design, especially focusing on the durability criteria in detail, in which we saw the most critical table, that is table 5 of IS 456. Then we talked about mixture design steps as per IS 10262, which were divided into 9 steps, starting from determining the target strength up till correction of water content based on moisture content of aggregate. We also solved a numerical to understand the application of these steps. Then we talked about mixture design based on DOE method, which is commonly practiced British standard method for mixture design. For this also we talked about different steps of mixture design and saw how the derived relationships or tables mentioned in the British standard code is used in each step of mixture design. So at last we ended with the unsolved numerical of for mixture design based on DOE method. So let's start our session today first by solving this previous question and then we'll move ahead. So what question says, we need to design a concrete mix for a targeted 28 days cube strength of 45 MPa from the following data using DOE method. So we know the maximum size of uncrushed aggregate to be used is 20 mm. We need to prepare a low workability mix having slump in the range of 10 to 30 mm. Specific gravity of aggregate is given to us, which is 2.65. Aggregate passing through 600 micron is 60%. Exposure to concrete is moderate, and cover to the reinforcement to be provided is 25 mm, that is mentioned to us. Okay, so here my first step will be to determine the target mean strength. Okay, so I the target mean strength I am denoting by TMS will be equal to nothing but FCK plus 1.65 times standard deviation, which I am assuming as 5, because that we can take from IS provision also. Or if it is not given, if we don't want to use the IS code, then question must give to us, or we must have some experimental data where we have determined the standard deviation. So for now I am taking it as 5. So 45 plus 1.65 times 5, it will give me 53.25 MPa. So this is my target mean strength for which I want to design. I heard some beep coming. Yes, last class we talked about mixture design based on IS 10262. Today we'll talk about first DOE method, and then we'll talk about ACI method.
Sir, for concrete mix design as per IS code, might be you have referred the 2009 code because it is now revised into 2019, right, sir?
So that's why we mentioned that correction last time when that slump correction I mentioned to you. Like earlier, it was 20 for each 50 increase, and then we talked about saw the correction and we designed for every 25 increase slump. So that correction we have seen.
That is also there. When we have to go for the selection of water cement ratio, there is a one curve in IS
So
2019.
see, the basic step of design is the same. The code may have provided a new water to cement ratio curve that you can use, but the basic step will be the same. So if you can read both the codes and you can practice on yourself also. Like it won't be possible that every time I will teach you each code again and again if there's some provision improve like new code that came up. I am just following the say discussion that was there in the NPTEL course and making the things look the same as there was in the discussion. You can read the code, and whatever changes are there you can learn the changes and implement, but the base structure, how to solve a numerical while understanding what all data we require, that will be the same.
Yes, sir. Actually, that NPTEL, I think it is a whatever the NPTEL courses uploaded for concrete
See,
technology. It
this
is 10
things
years
we will
before it is.
discuss at the end. Okay, let's first move ahead with the session right now today,
Okay, sir.
and then
Okay,
at
sir.
the end you can ask these
Okay, sir.
questions.
Yes, sir.
Okay, so we have seen the first step, that is target mean strength estimation. Now, step 2 will be to determine the to select a water to cement ratio. Okay, that is step 2 is to estimate the water to cement ratio. Okay, so for this we will use the DOI chart that we saw last time. So I will just take that chart from the last class that we saw. Okay, so this was the chart that we saw, and there was one table also. So I will just copy it temporarily so that you can have a look. Okay, so we will use these two tables, the charts as reference. So we have cement type 1. I'm assuming that we are using cement type 1 since there is no specific requirement mentioned in the question. And we have uncrushed coarse aggregate. Okay, so for these two, For a W by C ratio of 0.5, we can see the strength value will be 42 MPa as per the table. Okay, at 28 days. Now, what I want a strength value of 53.25 MPa. So, for this, we'll go to the chart now. So, in chart, what we'll do, so we'll first draw a line at vertical to 20, zero point 0.5 ratio. Okay, so we'll first draw a vertical line from zero point 0.5 like this. Okay, and we will draw a line from 0.42 ratio like this, and we will find the point of intersection which is coming around like here. Now through this point of intersection we will draw a parallel curve like this, and then for a strength value of 53.25, which will come somewhere here, will determine the W by C ratio. So you can use a proper like line tool to do this calculation. Okay, so when you will try to project it downwards in a straight manner, you will see it will come out to be somewhere here. Okay, so this value will correspond to a W by C ratio of, I'm assuming this value will come out to be like WSY required will come out as suppose 0.42. Okay, just around this point, so it can be close to 0.42 or 0.43 something, so I'm taking it as 0.42. Okay, so we have determined our required W by C ratio. Now step 3. So step 3 will be determination of water content. Okay, for this again we need to use the chart, reference chart that are there in DOE method. So we have this chart. Okay, so what this chart says, okay, I have 20 mm maximum aggregate size and I need low workability. Okay, that is given in to us in the question of 10 to 30 slump. Okay, so for this, if I see in the table, this is my value of 20 and low workability 10 to 30 uncrushed aggregate. It will give me a estimated water content of 160 kg. So my estimated water content is coming out to be 160 kg. Now, since it is mentioned that we have a moderate exposure condition, okay, so maximum WIC ratio allowed is that also we need to check. So for that we'll use this table, that is to check the maximum W by C ratio. So you can see for a moderate condition, we have a maximum W by C ratio that we can go up till is zero point 0.6. But since we are taking 0.42, so we are under the acceptable range. So we are okay with the proportion that we have taken. Okay, so we don't need to change anything for that. Okay, whatever we have taken, it is acceptable. Now, step 4 is determination of cement content. Okay, so I know my water content is 160 and my WAC ratio is 0.42. So 160 upon 0.42 will give me cement content, and that will come out to be around 381 kg. So this is my cement content. Okay. Again, we can check with the table what is the durability criteria. So in this table, you can see for moderate condition, durability criteria says minimum cement content required is 300 kg. So we are well above that value, so it is okay, we can go with the 381 kg cement content. Okay, so this is how we determine the cement content. Now step 5 will be determination of total aggregate content. Okay, so we have free water is 160 kg, and we know specific gravity of aggregate that is given to us is 2.65 kg. So what we'll do, we'll again use the curve that is given in the DOE method. So you can see this curve, I will copy it here. So in this curve, for a 2.65 kg will lie somewhere in between. So what we'll do, we'll just draw a one vertical line first, okay, through 160 kg, and then suppose my 2.665 curve will lie somewhere in between. Okay, so here somewhere in between my 2.65 curve will lie like this. Okay, so this is my point of intersection, and through this point of intersection I will draw, I will project it on the y-axis, and I will see where it is interacting with the y-axis. So if you see here, it will interact close to this point, which is in between
सर
2400 and 2500.
सर आपका मार्किंग तो 2.55 से हुआ है लग रहा है.
No, this is 2.5, this is 2.6, and this will be around 2.65. See the values here. 2.5 is here, 2.6 is here. Let me zoom the screen, na, then you will understand. See, this is 2.5, this is 2.6, this is 2.7. So for 2.65, the curve will lie, the line will lie somewhere in between that I have drawn. Is it clear?
यस सर, यस सर.
Okay, so this value will be close to around, I'm taking it as the midpoint. Okay, so we will take the value of wet density of concrete as 2450. Okay, so wet density of concrete is 2450 kg per meter cube that we have determined. Okay, so once we have determined the wet density of concrete, the total aggregate content we can determine as total density, that is 2450, minus uh, cement content, that is 381 kg per meter cube, and minus water content, that is 160 kg per meter cube. So this will give me the total aggregate proportion, so that is 1909 kg per meter cube of concrete I need to take the aggregate. Okay, so this is the value of total aggregate content that I can determine now. Now the next step, now we know the total aggregate content, so our next step will be to determine the fine and the coarse aggregate content. So step 6 is determination of fine and coarse aggregate content. Okay, so we know we have 20 maximum particle size, we have W by C ratio equal to 0.42, and it is given to us in the question, aggregate passing through 600 micron is 60%. So these three things are given to us, and we know the slump that we require is in the range of 10 to 30 Okay, so these all things we know now. So for that we'll go to these tables. So table 1 was for 10 maximum aggregate size, this was for 20 table, this set of curves, second set of curve was for 20 and this third set of curve was for 40 so we need to use this second set of curve. Okay, so I will just copy that diagram, and I will crop the bottom half so that there is no confusion. So this is the set of curve that we need to use for 20 mm aggregate size. Okay, so here we'll use this second curve. Okay, I will again zoom the screen and use the marker. So we'll use this curve for 10 to 30 slum, and we have given percentage passing at 60. So this is the required curve that we need to use. Okay, so we have a w by c ratio of 0.42, which will lie somewhere here, and it will interact at this point, and from this point if we'll project here, we'll get a value of very close to 30%. If you can see, it is close to 28 to 30% you will get the value. Okay, so what we'll do, we'll assume right now as 30%. If for more accuracy you can take 28%, 29% also, but for now, for simplicity in the calculation, I'm taking this as very close to 30%, so I will take the value as 30%. Okay, so this is how we'll determine the fine content. So fine aggregate proportion in total aggregate is 30%, and the coarse aggregate is 70%. Okay, so we know the total volume of aggregate. So fine aggregate will be zero point 0.3 times 1909, which will come out to be 572.7 kg, and coarse aggregate is zero point 0.7 times 1909, so that will come out to be 1336 kg. Okay, so this is how we determine all the proportions. So we now know the content of fine aggregate, we know the content of coarse aggregate, we know the water content, cement content, we know the W by C ratio, we know the water content, and thus we have calculated all the values. If there was some moisture content given in the question, so at last we can do the moisture correction also, but since that data is not given to us in the question, or we have already practiced that thing how to use the moisture content in the previous question, so I have skipped that thing for now in this question, but you can do that also at the end if you want. Okay, if you have the moisture content data, we can use the same formula that we discussed for the is code. Okay, so this is how we use different charts and relationships mentioned in DOE method for calculating the mixture proportion. Okay, any doubts in this part? Okay, let's move ahead then. I will close this week 5. Now, after Indian standard method and British standard method, we have ACI method. So, the ACI method is a widely used procedure for designing mixture concrete mixture, which is developed by American Concrete Institute. Okay, now before starting with the steps involved in the ACI method for mixture design, we must know some basic information of raw material which we are using, and concrete that we need to prepare as per the requirements of ACI 211 method. Okay, so these information includes required compressive strength of concrete. So we should know what compressive strength we require, as we have done in all other mixture design also. We need to have data for sieve analysis of fine and coarse aggregate. We need to have a data for bulk specific gravities and water absorption and moisture content of aggregates. We need to have data of specific gravities of Portland cement and any other cementitious material, and we need to have a relationship between strength and water to cement ratio for available combination of cement and other cementitious material if considered. So, though I have mentioned here these basics requirements that are needed for ACI method, these requirements are generally needed for any mixture design, which is like applicable for any mixture design. These all things we need to know before applying, before doing proportioning for using a mixture design code. Okay. So this slide shows the list of steps that are involved in the mixture design as per ACI method. So step one, as usual, is the calculation of target mean strength. So we know the characteristic compressive strength that we require, and we'll do the calculation of target mean strength. Okay. Step two is the choice of workability level. So if we don't know what slump is required, then based on the concrete component and its need, we need to adopt an appropriate level of workability as per ACI method. Okay. Step 3 is the selection of maximum aggregate size. Again, unlike other codes where we already have this information of maximum aggregate size, ACI code says that selection should be made based on the dimension of concrete element, concrete member, and the spacing between the reinforcement bar. So for that, code has given some rules that we need to follow, that we'll see. Step 4 is the determination of W by C ratio, which we will see is done based on the empirical relationship between strength and W by C ratio given in ACI 211 guidelines. Step 5 is the determination of amount of mixing water and air. Here, air is a additional parameter to be determined. Like unlike IAS and DOE method, where we assume that there is no air void inside concrete, ACI method provides value for percentage air void in the concrete also, for both conventional concrete and air entrained concrete. Step 7 is the determination of cement content, and step 6 is the determination of cement content. Step 7 is the determination of fine and coarse aggregate content, which is based on slump value and fineness modulus of sand, which we'll see in coming slide. And final step is the adjustment made for the consideration of moisture content in aggregates. So as we saw here in step 2, which is a choice of workability level, so if slump is not specified, an appropriate value of workability level needs to be selected. Okay. For this, we have a table in ACI code where we have a range of slump required for different concrete application, as you can see here in this table. For example, suppose you want to prepare a reinforced concrete beam. Okay. So there in this table, it is mentioned the minimum and the maximum value of slump required. For the reinforced concrete beam, it is in the range of 25 mm to 100 mm. Now it is mentioned that we should aim for a middle value in the range. Okay, so if we are planning to cast a reinforced concrete beam, we can select the slump to range from 50 to 75 mm as the target slump for achieving a required workability. Okay, so this is how we read this table for making the choice of workability level. Then, for selection of maximum aggregate size, the selection is made based on the dimension of concrete member and the spacing between the reinforcement bar. So, commonly, the maximum aggregate size should be the largest that is economically available and consistent with the dimension of the substructural element. And ACI 211 code specifies that the maximum aggregate size shall not surpass one fifth of the narrowest dimension between the sides of the foam. So suppose this is my one foam and this is my second foam. So maximum aggregate size should be less than one fifth of this total dimension. Okay, it should be less than one third of the depth of slab, and it should be less than three fourth of the minimum clear spacing between individual reinforcement bar, bundle of bar, or pre-tensioning strands. Okay, so based on these value, we will know what is the dimension of our concrete. Okay, sides, depth, and the spacing of reinforcement, that we'll know when we'll design RC element. Now, for designing the concrete mix for that RC element, we need to take these criteria first from dimension and check whether our maximum aggregate size that we are taking is passing these criteria or not. Okay. Now, for determining the water to cement ratio, there are two tables in ACI code. There's table 3, which shows the relationship between the average compressive strength and the water to cement ratio for both conventional concrete, that is non air entrained concrete, and air entrained concrete. And there is table 4, which shows the limit of maximum water to cement ratio to be used for concrete exposed to harsh conditions. Okay, this same table 3 has been shown here in the figure also, which shows the how strength versus water to cement ratio is varying for both non and conventional concrete, that is non air entrained concrete, and air entrant concrete. Then, using table 2 in ACI 211, we will determine the amount of mixing water and the air voids. So, for this, we require slump and maximum aggregate size data. Okay. Suppose, like for example, suppose I am preparing a conventional concrete and I want a slump of in the range of 80 to 100 mm, and I have a maximum aggregate size of 20 MSA. So what this code says, I need to take my water content as 200 kg per meter cube, and I need to ensure that I need to assume that there is 2% entrapped air in my concrete. Now, similarly, suppose I want to prepare a air entrained concrete with the same slump demand of 80 to 100 and the same maximum aggregate size. So my water content that I need to take now will change to 180 kg per meter cube. And if the condition is extreme for freeze and thaw action, then I need to take my I need to entrain 6% of air void. Okay, how to fix this 6% in concrete? For this, we'll use air entraining admixtures. Okay, that we have already discussed earlier. Okay, how we introduce air voids in concrete using air entraining admixture, and these becomes critical in freeze thaw application. Okay, so this is how reading this table will change for a non air entrained concrete and a air entrained concrete. After this, we have table 5 in ACI 211 for to determine the ratio of coarse aggregate in total aggregate, knowing the maximum aggregate size and the fineness modulus of fine aggregate. So you can see here, these are the fineness modulus of fine aggregate, and this is the maximum aggregate size. So again, suppose I have a 20 maximum aggregate size and a fineness modulus of 2.8, then I need to take 0.62 ratio of coarse aggregate in the total aggregate volume. Once we know the coarse aggregate volume, we can easily determine the fine aggregate volume. So this is how we design a mixture design. We prepare a mixture design as per ACI 211 method. Okay. Now let's see a numerical again, just to see the application of this code. Okay, so this is the numerical that I have. Try to read this numerical once and try to solve on your own, and then I will tell you how to solve this question. So just note down all these values and think about all the tables that we have just saw, and within a minute we'll start solving the question. Till that, you can ask your doubts if you have any doubts in the design steps that we have discussed for ACI method. So are there any doubts?
Sir, there's one doubt, sir.
Okay.
In the slide, what professor was telling, sir, for this ACI method,
Yes.
at the starting, sir, at time 3.13, there is one chart for the non-entrained air,
Yes.
wherein the slump in centimeter was the range was 2.5 to 5, then 7.5 to 10, then 15 to 17.5.
Is it? I need to check that, because these tables I have taken directly from the ACI code. So
Okay.
maybe he might have used an earlier code which was not updated. I need to check that once.
Because, sir, based on that, because while solving the assignment now,
Okay.
again at 32 minutes, the when he sir was explaining about a numerical,
Okay.
the values are changing, sir. For this different slum has been given, and the non-entrained air, that is, the values are different again.
Okay. So there is one question like this in the assignment where you are not getting the same value because of change in the code
I
with
got it,
provision.
but there are two different table and got confused into which table to be used, because in one of the slum, in one of the table in the initial 3 minutes,
Okay.
the slum value is in the range of 2.5 to 5.
Okay.
Whereas at 32 minutes, the same slump value has changed from 3 to 5.
Okay. Let's see that thing. What is the error in the that like discussion part? We'll see that thing at the end of the session. Okay.
Okay.
For now,
Okay.
you just refer to these tables that I have given. Na? This I am directly taken from the ACA standard. Maybe there is some confusion in the slide that will I will try to clear you at the end. But to everyone I'm saying this same point. See, right now for you it is important to understand the steps. Okay, the table which professor has referred, or like it can since the sessions that are uploaded on NPTEL is not a fresh session, it's a fresh session, it is uploaded way back. Okay, so might be there is change in provision because of which the values are changing. So that thing we can see, we can update ourselves by reading to the latest code. But the steps how to design a concrete mix will be the same. Okay, so what for now what we'll do, we know the mixture design steps, and we know a specific set of tables that are mentioned in the ACI code. We will follow that and we'll do the mixture design. Whatever problem you are encountering in the assignment, that we'll see at the end. So I will tell you how to solve that thing, or how you can go ahead uh, asking NPTEL team or for any correction if you need. Okay.
Sir, same thing, sir. That assignment answers are not matching with the our calculation
Okay.
because of the
This
code
question
reference,
I
I
have
think.
seen, one someone has mentioned one question assignment 5 question 2. I guess again that problem would be coming. So we'll see at this question at the end. Okay.
Yes, okay, sir.
Okay. For now, let's see the solution of this mixture design problem. Okay. So again, our step one remains the same. Okay. That is determination of target mean strength. Okay. So I'm assuming a standard deviation of 5 MPa. Okay. So my target mean strength value will come out to be 30 plus 1.34 times 5. So it will be equal to 36.7 MPa. Okay, so this is my target mean strength that I need to design for. Now the second step will be step 2 is choice of workability level. Okay, so what we have given in the question, it is given to us that the slum for which we need to design, it is already given to us is 50. But suppose this value is not given to us, we have also been given that we need to design a RC beam. So we have just seen earlier that for a RC beam, the slump required is in the range of 25 mm to 100 mm. And since we need to take an mid-range value, so it will come out to be 50 to 75 mm slump that we need to design for. And that is what we have given, that is what it is already given in the question. We need to design for a slump of 50 mm. Okay, so this is how can make the choice of workability. So though it is, we are getting it in the range of 50 to 75 mm, since in the question I have mentioned that the slump for which I am designing is 50, is required to be 50, so we can take directly 50 mm slump. Okay, for which this is a choice of workability level. Then the next step is the choice of maximum aggregate size. Now for choosing the maximum aggregate size, we need a proper dimension of RC beam, like width of sides, depth of section, everything, and the reinforcement diameter, the amount of reinforcement provided, the spacing between the reinforcement, everything. But for now, let us assume that the maximum aggregate size is 20 mm. Okay, for keeping this question particularly targeted towards the mixture design and not going into the complete design of the RCB. Okay, so that this calculation you can do very easily. Okay, when you will do a complete mixture design for a building or anything, you will have every section mentioned, like what is the length of my beam, what is the breadth of my beam, what is the depth of my beam, the amount of reinforcement that is there in the beam. Once you know all the values, you can just use these provisions that are mentioned: 1/5, 1/3, and 3/4. So 1/5 multiplied by the length, you will get one value. 1/3 multiplied by the depth, you will get one value, and 3/4 of the clear spacing between the reinforcement, you will get one value. So minimum of those values you can use as the maximum aggregate size. So for now I have taken the maximum aggregate size as 20 mm. Okay. Now step 4 is determination of W by C ratio. Okay. So we have seen in the table, for a non air entrained concrete having a compressive, so this table and this chart I will copy here. Okay, so for a non-air entrained concrete for which we need to design having a compressive strength of very close to 37 MPa. Okay, what W by C ratio we need to take? So for 40 MPa we have value as 0.43. For 35 MPa, we have value mentioned as 0.48. So 37 is lying somewhere in between 40 MPa and 35 MPa. So for 37 MPa, I can just do a normal interpolation like linear interpolation. We have 2 points, y1, y2, and x1, x2. So using that, we can do the interpolation, or either we can go to this curve. We can draw a vertical line, a horizontal line through 37 MPa. We can see where it is interacting this blue curve, and we can draw a vertical line to find the W by C ratio required. But for now, since my 37 MPa will lie in the mid range of 40 and 35, so I am assuming that the water to cement ratio will be close to 0.45. Okay. The same thing you can do from the graph also. You will get a value very close to 0.45. It will be somewhere 0.445 or 0.5455 in that order. So for taking a simple value, I'm assuming it to be as 0.45. Okay. Now step 5 is determination of amount of mixing water and air void. Okay. So my slump demand is 50 mm. Maximum aggregate size is 20 mm, and I need to prepare a non air entrained concrete. Okay, so water content, how we'll calculate? We'll go through the table. So you can see slump demand of 50 mm is somewhere lying in this order, and maximum aggregate size 20. So my water demand is 185 kg per meter cube. Okay, so my water content amount of mixing water is 185 kg per meter cube, and my entrapped air voids will be 2%. Okay, entrapped air voids is 2%. Okay, so this is how we determine the amount of mixing water and air voids. Now next step 6 is determination of cement content. So we know the water content, and we know the W by C ratio, that is 0.45. So water upon W by C ratio will give me the cement content. So this will come out to be approximately 411 kg per meter cube. Okay, simple division we can do. We can check this value for durability condition also. So suppose if in the question it is mentioned the exposure severity or exposure condition, we should check this value first whether it is lying in the durability criteria, whether it is under the limits of durability criteria or not, and then we need to go forward. Okay, for after step 6. Now step 7 is determination of coarse fine aggregate. Okay, so we have maximum aggregate size is 20 mm, and we have fineness of sand that is given to us is 2.80. So again we'll go to this table. So for 20 maximum aggregate size and 2.80 fineness, we have proportion of coarse aggregate is 0.62. Okay, so my coarse aggregate proportion is 0.62 and my fine aggregate proportion will be equal to 1 minus 0.62, so that will come out to be 0.38. Okay, now first I need to determine the volume of total aggregates. Okay, so my volume of total aggregates will be nothing but total volume minus air voids, since I know amount of entrapped air in my concrete, so this I can take into account in this numerical, then cement volume, and then water volume. So assuming that I'm designing for a 1 meter cube concrete, my total volume is 1, then my air void is 2% of total volume, so 0.02 times 1. My cement volume will be 185 kg per meter cube. So this I will sorry 411 kg per meter cube. So 411 divided by density of cement, that will be nothing but 3.15 times 1000 is the specific gravity of water, and for water it will come out to be 185 divided by 1000. Okay, so when we'll do this calculation, the volume of total aggregates, it will come out to be 1 minus 0.02 minus 0.130 minus 0.185. Okay, so this factor will come out to be 0.665. Okay, so this is the volume of total aggregate. Once we know the volume of total aggregate, we can determine the coarse aggregate volume as 0.665 times 0.62. So this is my proportion of coarse aggregate. Volume I know, so mass will be nothing but specific gravity into density. So it will come out to be 1105 kg per meter cube, and volume of fine aggregate similarly will be 0.665 times 0.38 times specific gravity of fine aggregate, that is given to us as 2.65 times 1000. So this value will come out to be 669.6 kg per meter cube. Okay, so this is how we determine both the was we determine the proportion of each uh, component in a mixture design as per ACI standard. Now there is one more step that is there for us to do, that is moisture content and moisture content correction. So we know the moisture content in aggregates right now, so this will be opposite. Okay, this is the absorption capacity. Okay, total absorption capacity, and this is the moisture content. Okay, because moisture content can't be more than the absorption capacity, so we know this is the maximum absorption capacity of my aggregates, and this is currently the moisture content present in the aggregates. So for this we need to apply the correction. Okay, so once I will show you this correction, because we haven't seen this correction earlier, both the things together. Okay, so we know these proportions till now. Now final step, that is step 8, is moisture correction. Okay, so additional water required for coarse aggregate will be the total volume of coarse aggregate into the total absorption capacity of aggregate minus moisture that is already present in the aggregate. Okay, so this difference is the amount of water my aggregate will take up. Right now 0.5% is there in the aggregate, and it can take 0.5% more, so that's why I have mentioned 1 minus 0.5%. So this value will come out to be 5.53 kg. Similarly, for fine aggregate, we can do, it will be 669.6 times 2% minus 1%. Okay, so there in the question it is given to us 2% is the absorption capacity and 1% is the moisture content right now in the aggregates. So this will give me the value of 6.69 kg. So total water that I had 185 kg per meter cube. I need to add 5.53 kg for coarse aggregate and 6.69 kg for fine aggregate so that I can get my aggregates in SSD state. And whatever water here that is mentioned 185, it is the free water that is there in the concrete. Okay, so for now, we need to correct for the aggregate volume also, since when we design, we assume aggregate in SSD state, but the aggregates that we have is not actually in SSD state. So for that, we need to do the correction. So corrected aggregate volume will be nothing but 1105, the volume that we have right now, plus getting the aggregates first, removing the moistures from the aggregates. So 5% I will remove from the aggregates, and then I will get the aggregate into the SSD state. So I will add the absorption capacity of aggregate. So 1 minus 0.5% plus 1%. Okay, so that will get my aggregates in the SSD state. So this will come out to be 1110.5 kg per meter cube. Similarly, for fine aggregate volume, again, what I need to do first, I will dry off my aggregates. So 1 minus what is the moisture content in the aggregate right now, that is 1%. So I have subtracted 1%. Now my aggregates are dry, and now I'm adding the total absorption capacity of fine aggregate, that is 2%. So plus 0.02. Okay, so this will get me the value of 676.3 kg per meter cube. So this is how we do the moisture correction for both water and aggregate volume. Okay, and these are the steps for mixture design of as per ACI standard. Any doubt in this mixture design calculation?
Sir, if two sets of standard deviation values are given, then how to calculate the target strength?
What two sets are given? Like, I didn't understand the
Like,
question.
no, so while we are calculating the target mean strength, we want standard deviation, right, sir?
Yes, yes, yes.
So for standard deviations, we have minimum 30 set of the sample we need to do the trials.
Yes,
So based upon the 30 sets of the samples, we have to calculate the standard deviations. If
yes.
two sets are given,
Two sets, like two 30 sets of sample.
one set is 15 and another is 15.
So like the
Then
samples
how to
are
calculate
obtained
the
from the
target mean
same
strength?
site, or those are like different sites.
Same cycle.
So then you can mix the sample. Na total you have 30 samples. What is the issue?
Okay. So then you can add both the values, then you can take the final value
No,
for
no,
the
no.
standard deviation.
See, for 15 samples, you know the compressive strength. Okay.
Okay.
And for more 15 samples, you know the compressive strength. Okay.
Okay,
Total
sir.
30 samples you have collected from the same site. Okay. So you
Okay.
have 30 samples in total. For these 30 samples, first calculate the mean value, and using that mean value,
Okay.
calculate the standard deviation of for the entire 30 sets. That you can use at the as the standard deviation.
Okay. Sir, again, formula will be same for the target strength, that is 1.34 into S, or the formula is going to change.
No, that will thing will be the same. Okay, 1.34
Right.
times is this should be 1.34. I guess there it was mentioned incorrectly.
Because in
No,
regular lecture, the professor has given the two formulas to
which two
calculate the target mean
formulas?
strength. I think one is for 30 sets of sample, and another is the two sets of sample.
Let me check that thing. Generally, we need minimum 30 sets of sample to calculate standard deviation. If we don't have 30
Even,
set of standard samples, then we need to assume value that are mentioned in the code. Okay,
yeah,
so that is the
because
rule.
that, yeah, that question asked in the assignment question, sir. That's the I got confusion, so that I asked this.
Okay, let me see that question, what that question is actually mentioning, and then I will answer you. At the end, let's see that question also.
Okay, sir. Okay, sir. Okay.
There was someone else also in between who was trying to ask something.
Sir, what recently sir has asked and what professor was telling in the lecture, sir, there are two standard deviations. When there are two standard deviations given,
Okay.
at that time we need to take the square of both of them and do the under root of it.
Okay, let me see that question. Na. Let me read that question once and then I will tell you because like this I won't understand. Like each one of
Yes,
you
yes,
was
sir.
trying
Because
to
what,
explain in a different way. Na. So let me read the question once.
sir, because what you taught is completely different from what professor has taught in the lecture, sir.
See, generally the process is you need to have minimum 30 sets of sample. Okay, for calculating standard deviation. If you don't have 30 sets of sample, then the values that are given in the code that you can assume as the standard deviation. This is the general case. This is not something that I am teaching. This is the usual case how we do the design. Okay, this question like desired 20-day compressor strength. Okay, so what is this question about that someone has posted in the chat box?
Yeah, sir. Based upon the ACI method, we have to do the mixed design.
So you can do na, you know all the values. I have taught you right now how the calculation is done. Try to attempt
Question
this
is here.
question. Try to attempt this question. Na? Now you know how we proceed on with the ACI method application. Na? So this you need to try on your own because since
Sir,
this is a assignment question and get to be submitted, I can't tell you the answers directly right now. Maybe next week, if you are not able to find the answer and if your answer is not matching the actual answer mentioned by the NPTEL, then I will tell you what is the solution.
no, sir. The issue is what you have taught is completely different from what, because here it is 28 days cylindrical compressive strength.
So
So
that
the
you need
entire,
to convert na. From
so,
cylindrical compressive strength, you need to convert to cube compressive strength. That is
sir, after,
actually
yes,
we.
sir. After converting,
Huh,
again we have another parameters to compare it.
okay.
So that is if the FC what we are getting, if it is less than 20.7,
Hmm.
then FC plus 6.9, and if it is in the range of 20.7 to 34.5, then we need to add FC plus 8.3.
Okay, so that set of standard deviation you're talking, huh? I've seen that thing. Okay, okay, I got your point. Okay, so those standard deviation, okay, if it is mentioned in the, I actually when I refer to the ACI code, I didn't found that table. Let me check that thing once. Okay, let me get you an update on that. But generally, we fix the standard deviation like this only. Let me check on that. Okay, let me see where it is mentioned in the ACI code, and if it is mentioned somewhere specifically, I will share you the code itself, so that rather than depending on some lines that are mentioned in some lecture or some slide, you can directly refer to the code properly. Okay, let me check that thing.
And in the same question, sir, if you see what one of the sir has posted,
Okay.
is the minimum cement content has already been stated and given to us. It is 300 kg per meter cube,
So it is given, so it is okay, na? So if it has
and
mentioned, that is the durability criteria you need to obey to.
the allowable water content is zero point 0.5.
So that is also okay. What is the issue in that?
No, sir. But in one of the question, what in the first step we determine is free water content.
Yes,
So that free
that
water
is
content,
not allowable water content. It will be allowable water to cement ratio. Maximum allowable water to cement ratio. It might be a misprint in the question. Okay, generally when we talk about durability limits, it is minimum cement content, minimum concrete grade, and maximum allowable water to cement ratio. It is never like maximum allowable water. Okay, because my water to cement ratio is actually governing my void percent inside concrete, which can govern my durability and concrete performance. That's why it is water to cement ratio, cement content, and concrete grade. Okay, so that correction you can like assume on your own. It won't be water content, it will be water to cement ratio.
That's why we got confused. I got confused basically because it's maximum available water content written.
That you can correct. Water to cement ratio. See, I think there are many doubts in the this part. So let's see this is at the end. Okay, I will open the assignment page and I will check what all questions you are mentioning.
Okay, sir.
For now, just remember the steps. Okay, that standard deviation thing we'll see, and rather all things I guess it will be the same. Just the standard deviation problem I will solve at the end. I will see what is the thing that is mentioned.
And sir, in one of the slide, professor was trying to tell this FCY is equal to zero point 0.8 of FCU. That is basically the compressive strength of the cylinder is almost equal to zero point 0.8 of the cube.
Okay.
So if we have some cylindrical compressive strength between any two different values, so we need to do the interpolation for that, sir, for the non-entrained air.
Generally, when we do the FCK estimation, na, we estimate the compressive strength of 150 mm cube. Like I will tell you as per Indian standard what we practice. Okay, so what Indian standard says, you need to determine the characteristic compressive strength of 150 mm cube. Whenever there is a cylinder given, we multiply it by a factor of 1.25 times to get the compressive strength value in terms of cube. So that is like a type of conversion we need to do to convert from cylinder to cube. Okay, because the same grade of concrete in cylinder will give me some other value of strength, and in cube it will give me some other value of strength due to change in the failure pattern. Okay, so that's why those conversions are mentioned, so that every value, every time my value can be reported in a specific dimension of testing. Okay. Am I audible?
Yes, sir. Can you show the first step, sir, the calculation step, sir, of yours?
So see, we were given in the question. Okay, I haven't mentioned cube or cylinder as such, but okay. So first step was target mean strength calculation. Here I will try to see what is the doubt in standard deviation. Okay, and then remaining steps were the same like what is mentioned in the ACI guideline, or what I guess was taught in the professor's lecture.
Basically, sir, yes. First is the standard deviation. Two different standard deviations have been given,
Hmm.
and then secondly, the cylindrical compressive strength was given, which was to be converted into the cube strength,
Hmm. That
and
thing,
then
that doubt we'll see at the end. Okay, that both the things we can see at the end in the step one of the calculation. What was the issue?
yes, sir. And after that, there are three parameters which professor had told to compare for the new compressive strength which has come. That is the mean cylindrical compressive strength which we are.
That also someone mentioned. Na, that thing also we'll see. Okay, I need to open the lecture slide one so that I can just connect with you what you are saying and how it is mentioned in the slide.
Okay, sir.
Okay, so let's move ahead. Now, since we have seen all three commonly practiced mixture design codes, that is IS method, DOE method, and ACI method. This table I have just created just to look at the comparison between them, like how each of these code operate. Okay, so if we see in terms of target strength, each code has the similar approach. Every code, they calculate target mean strength based on strength requirement and standard deviation. Okay, for water to cement ratio, my IS code, it determines strength versus W by C ratio and durability requirement. DOE method also depends upon strength and workability requirement, and ACI method depends upon strength and exposure condition, that is again durability requirement. Okay, for water content, IS code mentions that we need to use slump value, exposure condition, and workability as the critical as the parameter to determine water content. In DOE method, we have workability and maximum aggregate size as the deciding parameter, and in ACI code, we have slump, air content, and maximum aggregate size. So in this part, you can see difference comes when we see each code practice, how water content is determined. For cement content, all the codes have the same approach. We know the W by C ratio, we know the water content, and we know the durability limits, so we can determine the cement content. For coarse aggregate content, again difference comes in between codes. Okay, so IS code, it uses the grading zone of fine aggregate and maximum particle size, maximum aggregate size to determine the coarse aggregate content. DOE method, it uses the grading limits and wet concrete density to determine the coarse aggregate content. And ACI method, it uses the maximum aggregate size and fineness modulus of fine aggregate to determine the aggregate proportion. Okay, then once you determine the coarse aggregate content, fine aggregate content is like similar in all the codes, subtracting the net volume of aggregate from the subtracting the coarse aggregate volume from the net aggregate volume. Okay, so each code has been designed for a different usage application. Like you can see, it is mentioned in the end. Okay, so IS code, it is mainly used for Indian projects where local conditions and material must be considered. Similarly, DOE codes, they are used for high strength concrete with optimized cement proportion, which are generally applicable in UK and Europe, and ACI codes are generally designed for concrete designs having air entrained concrete also, which is widely used in USA and international projects. So you can see each standard, it is based on its its location practice. In America, in USA and in American conditions, there are chances of air entraining agents requirement also. So that's why they have added air entraining guidelines in their mixture design. In DOE, they are concerned with more high strength concrete designing, so that's why the design is made accordingly. In Indian standards, we the design is made according to the conditions and the material requirement. Okay. Now, suppose what if I take the same raw material information and prepare a concrete mix with all three different standards. Okay, so suppose I have this problem statement that I need to prepare a concrete mix for a compressive strength of 25 MPa 20 days, and I have this information available. Okay, I know the maximum aggregate size, air content, specific gravity, moisture content, fineness content, and other values also you can use. These are just limited information that I have mentioned. Other required information one may assume as a fixed entity also. Okay, so this is like some kind of exercise for everyone. They can try to just for the same requirement try to do a mixture design using all three standards. Okay, for now, suppose designing is done and I have the proportion of cement, water, aggregate, and W by C ratio that I have shown in the table below. Okay, so can anyone explain me how this observed differences in the obtained mixture design, why there is observed differences, what are the key differences in the mixture design that we obtain from ACI code, IS code, and DOE method? Okay, can anyone tell me what difference they can see? What is the major difference that they can see for the same requirement? If I do a mixture design using different code, I'm getting some differences in the values. So, how these values are becoming different? What is the reason behind the differences?
Sir, I think in ACI method we got the less cement content because of the air entertainment.
But right now we don't need to require we are not required to design for a air entrained concrete. All are non air entrained concrete. One can say since ACI method has a less cement proportion and higher W by C proportion, you can say it is less conservative design. Okay, that one can mention it is less conservative. Okay, that is one point you can mention. IS code, it requires higher cement content compared to ACI, so that is more conservative, or they are more concerned about the durability. And in DOE method, you can see there is a comparatively higher cement content and a lower W by C ratio. Why? Because DOE method is generally targeted towards high strength concrete designing, and that's why their values that we obtain are very less conservative. Okay, it is more towards higher strength demand. Okay, and ACI maybe towards more durability demand. So that is how differences can come, how much they are giving preference to the strength and the durability criteria. In that way, some differences we can see in terms of the mixture proportions that we are using. IS code is lying in between AC and DOA. So there is a balance between both strength and durability, we can say, that is there in the IS code. While DOA is more concerned toward the durability, and ACI is more DOA is more concerned toward the strength, and ACI is more concerned towards the durability limits. Okay, so each method has its own advantage depending upon the region, the durability need, the cost consideration, and the strength uh, importance. Okay, so that's why we can spot some of the differences. Even if we take the same question, we can have a different proportioning that we can obtain in the final mixture proportion. Okay.
Sir, we'll get the same strength if you refer the different code.
Maybe not, maybe yes, because each code is designed for a specific region. So aggregate quality and all other cement quality, they can vary from region to region. There's cement that we are using in India, it won't be the same that is used in America or in Europe. So that quality of things can also differ. Na? The aggregates, the source of aggregate can differ. So things can differ from one location to other location. You can see here a WYC ratio of zero point 0.5 and 0.42, they won't give you the same strength. Okay. But still, we are obtaining a value like this because it is as per like I've just taken the same mixture proportion and made a design all using all the three codes, and this difference we can see. Maybe it is due to how much safety factor they are trying to take on achieving a particular value. Maybe that is the case.
Yes, yes. Okay, sir.
That's why we say when we are doing a mixture design, we need to follow that particular code relevant to that region. So that's why we generally, when we do a mixture design, we use IS 10262. We don't use DOE method or ACI method because those are specifically used for a particular region or location of application. Okay. Now let's move ahead. So till now, we have discussed all conventional forms of mixture design, which were based on one common aspect, that is strength and workability requirement, which was defined as a function of water to cement ratio at the core. Now we will look into a advanced form of mixture design that is based on packing density and rheology. So a mixture design of concrete that considers packing density and rheology is essential for optimizing workability, reducing porosity, and improving the mechanical property. So the core of this such mixture design is based on optimizing workability, reducing porosity, which in turn will improve the mechanical property. And how such mixture design work? So we know that concrete has a particulate nature. That means it is composed of particles or materials of different sizes. So In fresh state, the wet cement paste and aggregate forms the concrete. Now, enhancing the packing density of aggregate system will minimize the interstitial voids, and optimizing the cement paste, rheology of cement paste in terms of yield strength and viscosity will govern the flow behavior of fresh concrete, which can control the workability, pumpability, and segregation resistance. So in this way, we are getting both strength and workability. So strength using packing density and workability using rheology, we can get both the things optimized. Now, unlike other methods, there is no like standard codal provision or something for such mixture design. Rather, this is more based on laboratory trials and experiments, and thus such mixture design are often called advanced, and they are commonly used to prepare high performance concrete like a UHPC, ultra high performance concrete, which can have a strength of more than 100 MPa. So for such high strength, we don't have a codal provision. Like there is no mixture proportion designing we can do by code. For such, we need to go for laboratory trials and some advanced mixture design proportions, which is generally based on packing density and rheology. So the core of such mixture design is based on three steps. So step one is optimizing the aggregate combination using the concept of particle packing. Step two is to ensure that the paste content is just enough to provide required workability based on rheological concept. And step three is to optimize the paste combination for best flow, which requires both particle packing and rheology as the core concept for understanding. Now, particle packing is something we have already discussed in detail in our previous session. Okay, so if I just try to simplify this concept in an easy way, we can say instead of using a single sized aggregate and relying on the cement paste to fill the voids between the aggregate and make concrete compact, a system of multi sized aggregate ensures that larger voids between the coarse aggregates are filled by the subsequent finer aggregates. So, by optimizing the particle packing, or we can say aggregate packing, we can minimize the voids that are there in the aggregate skeleton, which can either reduce the paste demand or which can give us a more flowable concrete with the same paste content. Okay, so the same thing is written in this statement. Particle packing is done for optimized gradation, where a well graded combination of fine and coarse aggregate maximizes the particle pa- packing density and minimizes the air void. And the image also justifies this line, where we can see how a larger void percent in coarse aggregate, when it is mixed with the fine aggregate, smaller aggregate systems, they are reduced. Okay, so this is the base behind the particle packing concept that we have already seen. Now, how we achieve this optimized packing? So first we need to select the range of particle size that are available to us. Then we determine the packing density. Okay. So there are two theories behind determination of packing density. Okay, first is discrete approach, which was proposed by a scientist, author named Fornes in 1931. So this approach says that the densest packing will occur when the finer particles exactly fills the void between the larger particle. So densest packing occurs when the finer particle exactly fills the void space between the largest particle. So when this is achieved, then we say that the packing density is optimized. However, this approach has two major limitations, as this that we have already seen earlier. That as the size of fine aggregate will approach the coarse aggregate, there are two interactions that we have talked about. First was the wall effect, okay, which we saw was near the wall, where due to increase which increases the air voids in the packing near the wall that we talked earlier. And one is the loosening effect. So suppose my fine aggregate are not exactly fitting into the voids between the coarse aggregates. So what they can do, they can disturb the packing of coarse aggregate, and instead of reducing the increasing the packing density, it can reduce the packing density. That is known as loosening effect. Okay, so that are the limitation of this approach when we talk about fine aggregate exactly fitting the void space within the larger aggregate. The second theory is the continuous approach, okay, which was proposed by Anderson in 1930. Okay, this approach says that densest packing is achieved assuming that the smaller particle are infinitely small. Okay, so this means that the void spaces between coarser aggregates shall be continuously filled by a finer aggregate size, like you can see in this image. So this is my coarse aggregate. The void between the coarse aggregate should be filled by the finer aggregates. The void between this finer aggregate proportion should be filled by a subsequent fine aggregate, then a subsequent fine aggregate, then a subsequent fine aggregate up till the smallest size. So this is known as continuous approach. Okay, after determining the packing density, we need to minimize the void content. Okay, for which packing density needs to be optimized. Okay, how to do this? So for this we need to adjust the proportion of different sizes like we saw earlier. We have, suppose I have two grades, 10 and 20 so I need to adjust the proportion of 10 and 20 such that I am getting the maximum packing density. If I will get the maximum packing density, the void content will be minimized. This we can see in this image also how to do. So this formula equation tells us that packing density in a multi-sized aggregate system is given by this formula: m1 by s1 plus m2 by s2 plus m3 by s3 upon total volume. So vc is the total volume of container, m1 m2 m3 is mass of each aggregate type, and s1 s2 s3 is the specific gravity corresponding to each aggregate. So using this concept, we can maximize the packing density once and minimize the void content. Once we have minimized the void content, we can optimize the paste volume to be more than the void content to ensure a specific workability requirement has been achieved. Okay, so this is generally a flow of how packing density is optimized in the aggregate system. So this figure shows like a contour map of a ternary aggregate system comprising of 20 aggregate, 12.5 aggregate, and river sand. So you can see how to read this table. So suppose I have this chart here. Okay, so when I will place this here, okay, so suppose I have zero point 0.3 as my volume of 20 aggregate, and zero point 0.4 is my volume of 12.5 aggregate, and zero point 0.3 is my factor of river sand. So when I take these proportions like this, 30%, 40%, and 30%, so my packing density will come out to be 0.64. Similarly, when I will change the proportion of aggregate, we can see how my packing density can change. So in this way, adjusting the proportions of our different aggregate size, we can get different packing density, and thus we can optimize our packing density by just adjusting the proportions of aggregate. So how to read this curve? So this line here shows how the line how we will make the projection of this side. For this side I need to follow horizontal line, and for this side I need to follow this kind of diagonal line. Okay, and the three interaction will tell me the area where my packing density will come. So this is something I took from one research paper where they tried to optimize packing density based on different proportion of three sizes of aggregate. Okay, so this is particularly known as packing density counter for various combinations of three size aggregate. Okay, so this is how packing density concept works. Now, based on this packing density understanding, try to answer these three questions. Okay. In the meantime, you can ask your doubts if you have any doubts regarding packing density. Though we have discussed packing density earlier, but still, if you have any doubts, you can ask here. Others, try to answer this question. Try to answer what will be the what. Try to answer this in the chat box. Okay, for first question, I'm getting the answer as A. So let's see the first question. The packing density of a granular material is influenced by the following factor. By which of the following factor? Particle size distribution, particle shape and texture, moisture content, and compaction factor. Okay, so the correct answer is C for this question. Okay, why? Because my particle size distribution for a well graded mix, I have a higher packing density due to better particle size distribution. So that's why particle size distribution can affect my packing density. Particle shape and texture, angular or a rough textured aggregate, they can increase the packing density compared to a rounded aggregate system. So that's how my particle shape and texture can affect the packing density. Moisture content, generally a smaller amount of moisture can improve the packing by reducing the friction between aggregates. Okay, but excessive moisture can lead to separation. So this is how moisture can also affect. So if there is less moisture, my surface will be rough, and rough surface can improve my particle packing. Okay, so moisture content can also contribute to particle packing. We can say it can contribute. Okay. And compaction is a direct answer. If we will do compaction, we will reduce the voids between the aggregates and we can improve the packing density. So this may be controversial to you, but it can improve the packing density. Okay, it can affect the packing density, but the other three are straightforward. Compaction means like externally we are using some rod or tamping instrument or vibration table, we are trying to compact a aggregate system. So if we will apply some external vibration, my aggregates will move and they will try to fill the spaces between each other, and it can also affect the packing density.
Sir, I have a small doubt, sir.
Yes.
Sir, how does this moisture? Because if you're telling it is dry, it will
So
help in
like
friction.
this is I'm saying that this can be true, cannot be true. Why I said moisture content can influence packing density? Because suppose I have a dry aggregates, so my surface is rough, so it may offer more friction to the aggregate motion while I am doing compaction, or it can offer more friction to aggregates, other aggregates also, which can influence my packing density. In that way, I said that moisture content can also influence. Okay, if my aggregate surface is wet, there is less friction between aggregates, so movement of aggregates will be much more easier. So that can affect how my particles are packing if I apply some compaction on it. Okay, so this
But
two
sir,
can go
the-
for line to line. Like when I
because
apply some compaction, then moisture can also play a role.
okay, sir. In one way, we can accept it because the volume or the space will remain the same thing.
Huh.
Whether the aggregate is fully saturated or whatever it is,
Hmm.
but the volume will not change. Whatever the space or the gap is there.
No, no, that won't change. I'm just talking about aggregate system right now, granular material, not a concrete where paste has also come.
Okay, sir.
So, like those who answered 1 and 2, they are also correct based on whatever we have discussed till now. 1 and 2 should be the correct answer. But here I have considered if I am applying some compaction also. So, how my packing density, will it influence my packing density or not? So, that's why answer can be 1, 2, 3, and 4 also. 1 and 2, those who answered 1 and 2, they are also correct. But these two factors can also play a role. Okay. For fourth question, can anyone tell me the answer? Second question, okay. I got one answer as D. Okay, let's see the question. For self compacting concrete, why is achieving higher packing density crucial? Okay, so the correct answer will be C, to reduce the need of excessive paste and improve stability. Okay, so when we talk about self-compacting concrete, so we need to reduce the excessive space to get better stability, so that we can reduce the shrinkage and improve the durability, and we can minimize some segregation and other issues, when we are doing vibration, or we can ensure uniform mix also. So in that way we can say higher packing density can help us. Okay, one more thing, suppose I have a higher packing density of aggregates, the amount of paste that is required to achieve a certain workability will be low. So the it may reduce the need of excess space that was required to achieve a certain workability. Suppose I want to achieve a workability of 150 mm. Now if my packing density is not optimized, I will require more paste compared to what I will require when my packing density of optimized. So that's why the answer is mentioned as it will reduce the need of excess paste and improve the stability. Can anyone tell me the answer for the third question?
Sir, in self-compacting concrete, do we need to have vibration, sir? Like what we do for normal concrete?
Generally we don't use vibration, so that's why I'm saying now, if we have a high packing density, then the paste that we'll require will be lower for achieving a particular workability.
Okay, sir. Basically, it is basically we need to have a good pumpability of the concrete also.
Yes, so if we have a higher packing density, then the amount of paste that we need to achieve a particular pumpability or workability of concrete will be reduced, and without requiring any vibration, so we can ensure a uniform mix without a need of vibration.
Okay, sir.
Okay, so for third question, in a ternary mixture containing fly ash, cement, and silica fume, which component primarily enhances the packing density? So it will be the silica fume because it is the finest. So silica fume is the ultra fine particle that fills the micro voids between cement and fly ash. So that may will play a critical role in like enhancing the packing density. Okay, because cement and fly ash, they have a particle size very close to each other, so silica fume will play a critical role in such cases. Okay. Okay, so let's move ahead then after these questions. So after packing density we have rheology. Okay, so rheology is like a fundamental property that governs the flow behavior of a fresh concrete. Okay, now understanding rheology is crucial because it directly affects the workability, pumpability, and resistance to segregation. Okay, also it helps us to determine how my concrete will behave when it before it hardens, so that which is important, which ensures that it can be placed, compacted, and finished properly. Okay, now when we talk about rheology, there are three main parameters that define rheological behavior of a concrete. Okay, first is yield stress. Okay, that represents the resistance to initial movement. Okay, so yield stress is like a minimum stress that is required to initiate the flow. So, like I have a pace system. What is the minimum stress that I need to apply on that pace so that it can flow? That is known as the yield stress. Okay, a concrete mix which has a high yield stress, it will be stiff. It will be difficult to work with. While a mix that has a low yield stress, it may lead to segregation. So we need to optimize the yield stress when we are talking about rheology. Second is plastic viscosity. So that is the resistance to flow once the material has started moving. So once we have crossed the yield stress, what is the resistance that my paste or concrete is offering to the flow? It is known as plastic viscosity. So basically, my plastic viscosity will determine how easily my concrete will flow under applied stress. Okay, a mix that has a high plastic viscosity, it will be sluggish, like it will be difficult to move. While a mix which has a low plastic viscosity, very low plastic viscosity, it will be like bleeding mix. Okay, so that's how my plastic viscosity will also govern my flow behavior. Third is thixotropy. Okay, so this refers to the time dependent stiffening behavior of my concrete. That means that after resting, my concrete will become stiff, but it can regain its flowability when I again remix it. Okay, so this property is essential for maintaining the shape while ensuring the ease of placement of concrete. Okay, so once my concrete is rest, then I will, when I apply again some force on the concrete, it will again become flowable. So this property of concrete is known as thixotropy, how with time my stiffening behavior is changing of concrete. Now, why rheology is important? Because it tells us about the fresh state behavior of concrete. Be- uh, be- like during compaction by vibration, my fresh concrete must yield easily. So when I'm compacting my concrete by vibration, so for movement I need to apply stress value which is more than the yield stress. Okay, so my fresh concrete must yield easily, okay, when due to vibration, so that it can deform under shear. Okay, and then it should also flow easily to attain desired shape. So my viscosity should be such that it can flow easily to achieve the desired shape while maintaining uniformity and cohesiveness. So there should be no segregation. So to ensure that all these activities occur, I need to understand the rheology. Okay. Now, to study rheological behavior, what we do, we analyze the shear stress versus shear strain profile of fresh concrete. This helps us to understand how my material what is the transition of material from rest state to a flowing state under stress. Okay, and by optimizing rheology, we can design a concrete mix which is easier to place, pump, and finish. Okay, so let's look at how this shear stress versus shear strain is related to different materials. So as you can see in this figure, I have a Newtonium fluid and I have a Bingham plastic material. Okay, so Newtonium fluid exhibits a linear relationship between shear stress and shear strain. Okay, which means that they will instantaneously flow under an applied stress. Okay, so you can see as soon as I apply some stress, there will be strain that will be there in my concrete system. Okay, so this such material is known as Newtonian fluid, and this such curve is applicable to a self-cementing concrete, self-compacting concrete. Okay, which flows under a small, even with the small stress application, the material will start to flow. Okay, so there is like zero yield stress for such material. However, for fresh concrete that we generally prepare, we that concrete follows a Bingham plastic nature. Okay, so what it means, the flow begins only when we exceed a certain yield stress. So when only when I will apply this certain amount of yield stress, then only the flow will start to happen. So curve is just for conventional concrete. Whatever we prepare, it follows a Bingham plastic nature. Now, mathematically, for liquids, shear stress and shear strain is related by this equation. So you can see this is shear stress and this is strain. Okay, shear strain rate. Okay, this is related by tau is equal to mu times del y by del t. Here mu is the viscosity. Okay, so in concrete, different rheological models helps us to describe different behavior. So the simplest model is known as the Newtonian fluid, but for practical application we use Bingham model. Okay, as it effectively captures both yield stress and plastic viscosity, which is key for understanding the how concrete flows and consolidates. Similar thing you can understand from this figure also, that we have already seen earlier when we talked about viscosity modifying admixture. So in the first case, you can see I have a high plastic viscosity concrete. Okay, so we can see initially my concrete is like this in my slump cone. Okay, once I remove my slump cone, it uh, collide. It takes some time to collapse. Okay, from going from this state to this state, it is taking some time. Like after 10 seconds, I can see it has completely collapsed, but after 5 seconds, it was still holding some shape because it has a higher viscosity. So it was offering more resistance to flow under gravity. However, if my concrete has a low plastic viscosity, you can see just after 5 seconds it will completely collapse because it has a low resistance to flow, so it was easily able to flow and it was collapsing. So it has a more flowability since it has a low plastic viscosity. So this is how viscosity can govern the flow behavior of my concrete. Now let's see how rheology defines my concrete. Okay, so in this figure, on the y-axis, I have yield stress, and on the x-axis, I have plastic viscosity. Okay. Now, suppose I have a reference case for which I know there is some yield stress and plastic viscosity. Okay. So, compared to this control, if my concrete is more viscous, so what will happen? My plastic viscosity will increase while my yield stress will remain the same. Like we saw in this diagram, for more viscous concrete, my plastic viscosity will increase. However, compared to reference, if my concrete mixture is more stiff, it is stiffer, then, or we can say it is less workable, then what will happen? For the same plastic viscosity, I will have a higher yield stress. Okay, so it will be more stiff if it has a higher yield stress. And compared to reference, if my concrete is wet, or we can say if it is more workable, then I will have both plus yield stress and plastic viscosity will be lower because I have more water in my system, or my system is more flowable, so it will reduce my yield stress also, and it will reduce my plastic viscosity also. So this is how both these parameter, yield stress and plastic viscosity, they can define the flowability of my flowability or workability of my concrete mix. The second figure also shows the similar understanding, where we can see what is the effect of paste, what is the effect of water, or addition of any mineral admixture. We can see how they are affecting the flow, workability, or rheology of my concrete. So similarly, how what we understood from here, we can apply it here also. Now, when we talk about a paste system, it is not just the binder composition and the W by C ratio that is there in the paste system. We also need to take care about an SP dosage. Like SP are very commonly used when we talk about making a workable concrete. So there is super plasticizers also that we need to be concerned with. So for cementitious material, combination can be optimized again by the concept of particle packing. However, for SP dosage to optimize, it is based on again rheology, which is measured in terms of two fundamental parameters, yield stress and plastic viscosity, and these properties are measured using two empirical testing. One is march cone test and one is mini slump test. This is, I am talking about SP. So suppose I have a cement paste, suppose I have a water to cement ratio of zero point 0.4 and cement content is 400 kg per meter cube. Okay, now I need to add SP to make this concrete flowable. But how much SP I need to add? Okay, and what is the limit above which I can't add SP anymore? So SP will work up till a certain limit. Okay, like suppose up till 1% it will give me a flowable concrete. Beyond 1% it won't give me much more improvement in the nature. So how to determine this 1%? How to determine the rheological property of SP? For this, we have these two tests, March cone and mini slump test. So you can see in this first figure, we have a mini slump test. So this is like a Wicca apparatus. Okay, it has a height of 40 mm and a specific diameter and a base diameter. So what we do, we will prepare a cement paste with a certain composition of SP. We'll fill in this paste and we'll raise this Wicca apparatus and we'll say see the spread diameter, we'll record the spread diameter. For different SP dosage, we'll do this thing and we'll see after what SP dosage we are not able to see increase in the paste diameter. So that will give me a knowledge about my what is the effect of SP dosage on the yield stress of my paste. Similarly, for plastic viscosity, we use this March cone test. So what we do, we prepare a cement paste. We fill 1 liter of cement paste inside this March cone, and we see how much time it is taking for my cement paste to fill a certain volume of this cylinder. Suppose 400 ml or 800 ml graduation we can mark on the cylinder, and we check with the change in SP dosage how the flowability of my paste is changing due to SP addition. So that change in fluidity will give me an idea about the plastic viscosity of my cement paste. So these two tests are very commonly used for optimizing my rheology of paste when a super plasticizer or a plasticizer is also used. Now try to answer these questions based on rheology. In the meantime, if you have any doubts, you can ask the questions.
Sir, regarding this SPs being added for the workability,
Yes.
so there might be so many companies across the entire world,
Hmm.
and different parameters might they might be using, or the chemicals might be using
Yes.
to get the
Yes.
workability.
Yes.
So, is there any laid down rules and regulations, or any codal provision that by using this super plasticizer we should achieve this much of workability or something like
See,
that?
this thing for each SP combination, this can change. Okay. With change in formulation of SP, that thing can change. So that's why we have these standard testing method which helps us to find how my SP dosage is affecting the flowability of my concrete. So whenever you see uh, some company which is supplying a super plasticizer, they have their own standard or they have their own dosage criteria that they mention, like you need to add this much percent SP if you want to achieve this much workability. Someone will say something else, someone will say something else. So it changes from SP formulation to formulation, and that's why there are standard test methods that are there to so that we can optimize the SP. Like suppose company says that you need to use 1% SP. Beyond that, it won't give effect. If you want to check whether it is true or not with your system or with your cement, you can do these testings.
But this percentage of SP might be changing for the strength of the concrete, what we are going to, the compressive strength, what we are going to desire also, sir.
No, SP we have already talked earlier if you remember. SP is concerned with the workability. Okay. Compressive strength can be affected. That is the secondary parameter that is affected by the W by C ratio, not by the SP. SP is governing the flowability, workability of my concrete. Suppose I have a W by C ratio fixed. Okay. Now I want to make my concrete more workable. So keeping the same W by C ratio and adding some SP, I can make a more workable mix, but my strength will remain the same. If I want to increase the compressive strength, I need to decrease the W by C ratio. And decreasing the W by C ratio, decreasing the water content can decrease my workability also. But since I want more workability, I'm adding SP. So SP's direct effect is on workability. But it can help us to make a low W by C ratio mix with the desired workability and more strength. So direct effect is on workability. Indirect effect is on strength.
Okay, sir.
You can refer to our discussion when we talked about chemical admixture. There was one slide in which I showed you, if I need to increase workability, what will happen? If I want to increase strength, what will happen? And if I want to maintain the same property, how SP dosage will play a role. So that slide you can refer once.
Okay, sir, I'll do that.
Okay, any answers to these three questions? So let's see. Okay, first, in a concrete mix, what is the primary cause of increase in yield stress? Yield stress. Okay, so answer will be higher aggregate course aggregate content. Why? Because as I will increase the course aggregate content, it will increase the internal friction and interparticle resistance between the aggregate, which can make my concrete harder for, like, more stiffer for initial flow. Okay, so it can increase the yield stress. SP dosage, if I will increase, it will reduce the yield stress. Higher temperature, it can indirectly affect because it will increase my like, it will increase the rate of reaction, so it may increase the strength gain, so it may reduce the workability and make my concrete stiffer. This is also correct. And increasing air void content, again, it will make my concrete more workable, so it may reduce the yield stress. But directly you can say aggregate content increase will increase the yield stress. Question number 7. A self-compacting concrete should ideally have which rheological characteristic? So, for a self-compacting concrete, it should easily flow without segregation and there should not be any excessive bleeding. So, we need a low yield stress and a moderate plastic viscosity. Okay. So, low yield stress will ensure that my concrete is easily flowing and filling in the formwork, and moderate plastic viscosity will help me to maintain cohesion between my aggregate and cement and prevent segregation. Okay, so I need to have a lower yield stress and moderate plastic viscosity. Question number 8. Which of the following best describes the effect of viscosity modifying admixtures in concrete? So the correct answer will be C. They increase the viscosity to prevent segregation. So viscosity modifying admixture, what they do, they increase the plastic viscosity without significantly affecting the yield stress. And this increase prevents the segregation, which ensures the stability and uniform mix. Like we saw here. Okay, it was increasing the plastic viscosity, which was increasing the resistance to flow. Okay, so these are the answers. Okay, so, like, I will stop here for this session because we need to discuss few of the assignment questions and it is already 8. So this next section, that is based on batching and mixing, we will start in the next session. That will be in continuation with everything there, like pumpability, transportation, batching, mixing, everything will come together. So we will have a, like, continuous understanding of all the post concrete operations. Okay, post mixture design operations. So for now, I'm stopping here. From slide 38, we'll start in the next session. Okay, so
Okay, sir.
we'll now stop for